Hi, I'm Jimmy, aka Perceptes. If you're new to the channel, welcome. I share electronic music performances and educational videos on music production, with an emphasis on hardware instruments and modular synthesis. In this video, we're going to explore ring modulation, a signal processing technique that combines two audio signals to produce a new one with strange clangorous overtones. In Eurorack, you can get a dedicated module to ring modulate two signals. We'll be using Intellijel Amps, a dual VCA with some extra features that give it ring modulation capabilities. It's no secret that Amps can do this. It's one of the patches suggested in the user manual. But we'll be looking at how Amps does it, and how you can do it with a combination of generic utility modules that you likely already have. If this sounds interesting to you, stick around. Ring modulation got its name from the original circuit that implemented it, which included a group of diodes that were arranged in a ring. I think it'll help to understand ring modulation fully by beginning with amplitude modulation, which is very similar. Now we know that if we modulate the amplitude of an audio signal, we're just controlling its volume. So as a basic example of that, I've got a sine wave coming out of the ONA oscillator going into the audio input of Intellijel Amps, which is a dual channel VCA. And then I've got an LFO, also a sine wave coming from plates that is going into the CV input of Intellijel Amps. And that is just modulating the amplitude of the incoming signal back and forth. If we listen to it, it sounds like this. So the green trace is our waveform coming in, the blue trace is our slow LFO going up and down, and the red trace is the final amplitude of the wave that's being passed through the VCA. Now this is simple, but if we increase the rate of that LFO so that it's actually an audio signal itself, then rather than just getting an audible sort of change in volume, we get a constant tone with new harmonics. Let's listen to that. So now you can see the green trace is what it was before, but the blue trace is now much faster and closer to the speed of the green trace. And you can see that the red trace is not really changing amplitude in sort of a slow up and down wave like it was before. It's relatively constant, although there's a lot of spikes in the waveform. The frequency of the sine wave coming from ONA is about 300 Hz, and the frequency of the sine wave coming from plates is about 100 Hz. Now, if we look at the spectrum analyzer, for that first wave from ONA, we can see that that vertical line on the frequency graph shows that there's a single harmonic that's at 300 Hz. And if we look at the graph for plates, we can see that harmonic at 100 Hz. And then if we look at the output of amps, which is the amplitude modulated signal, then we'll see something different. We see three harmonics. The first one and the one in the middle is the fundamental that's coming from ONA. If we tab back over to that, we'll see that that's the same harmonic. But in the amplitude modulated version, we have two additional harmonics, one above and one below the fundamental. And these are called sidebands. They're created by amplitude modulation. And the frequencies of those are the addition and the subtraction of the two waveforms. So because we have our 300 Hz fundamental and then a 100 Hz modulator signal, we get a sideband that's 100 Hz below and a sideband that's 100 Hz above. And that's what creates that combination of harmonics. Let's listen to what that sounds like. So it's a constant tone that kind of sounds like a chord. But the interesting thing is that if you change the fundamental, the distance of the sidebands away from that fundamental are the same. So even though increasing the octave of the fundamental doubles the frequency, the relative distance of the sidebands to that fundamental are the same. And so you get sort of different tonal relationships. Similarly, if we change the octave of the modulating wave, then we change the distance away from the fundamental of those sidebands. So that's amplitude modulation. Ring modulation is a very similar effect, and the only difference is that we want a wave that keeps those sideband harmonics, but eliminates the original fundamental, so we have only the sidebands. And the way that we achieve this with Intellijel Amps is through a clever combination of its extra features, which a lot of VCAs don't have. One of them is that the jacks on the left side will normal to the ones on the right side. So if you don't plug anything into the CVB, in B, or out B jacks, they will just get a copy of whatever is plugged into the equivalent jack on the left side. The two other features that are useful in creating ring modulation are this switch right here, which will invert the polarity of the second channel. So the waveform on the in B output will be an exact inversion of that. So every time that the input wave is positive voltage, it'll switch it to a negative voltage. So +1 will become -1, +2 will become -2, and so on. And then the next feature is that these middle toggle switches will change the polarity of the incoming CV signal. So when this switch is in the left position, it'll do the same thing as that polarity inversion switch for the audio, but for the CV signal. So again, positive values become the same value, but negative. And we can use those combinations of features to eliminate the fundamental while keeping the sidebands. Let me turn on the audio, and we can just hear it before we sort of break down how it works. If I simply move the output to output B, then we get ring modulation. You can see that those same two sidebands are there, but now the fundamental is gone. And as I move the fundamental around, the sidebands move. You can see where the fundamental might have been in between those two, but the fundamental is gone. And similarly, we can continue to change the bandwidth of the sidebands, but the fundamental is still not there. So why does this work? Well, it's a combination of the normaling and the inversion capabilities of amps. We're taking the original wave, and then we're mixing it with a copy of the wave, and that's what connecting only this second output does. The output A is getting mixed into output B, and those two waves are going off into our mixer together. The input signal is also getting mirrored across, and by flipping the switch, we are inverting the input signal. And as we know from phase cancellation, if you take a wave and the exact inversion of that wave and mix them together, you get silence. They cancel each other out, because when the voltage is high from one of them, the voltage is the exact opposite but low from the other one, and together they equal 0, which is silence. However, we don't want to invert the entire wave because that would also get rid of the sidebands. We only want to phase cancel the fundamental that's coming from the main input signal, and we want to keep the sidebands. So by inverting the CV signal, which is what's creating those sidebands, we sort of do like a double inversion where the sidebands are kept and only the fundamental is eliminated, which leaves us with this ring modulation. Okay, so what if you want ring modulation, but you don't have Intellijel Amps? You don't have something that has this fancy normaling and inversion features. Well, if we think about what those extra features actually are, they're fairly simple utilities that you probably already have. So normaling a signal from the left jack to the right jack is just multiplying it. So with a multiple, you can do the same thing. Inverting the CV and inverting the polarity of the input signal are actually exactly the same thing. It's just inverting. And so an inverter or an attenuverter can also do that. And then mixing the output A and the output B signals is just a mixer. And by no coincidence, those are exactly the modules that I have here on the right side of the case. The first one is SumDiff from ShackMat, which is actually a precision adder and multiplier, but one of the use cases for it is that you can use it as a buffered multiple. So the way it works is that it has two identical sections, AB and CD, and you can plug two signals into A and B, or likewise to C and D, and then the bottom jacks of each section will be the addition of the two signals and the subtraction of the two signals, A plus B and A minus B. But if you only plug something into the top jack and nothing into the bottom, then both of the bottom jacks here become just multiples of the top, because A plus 0 is A, and A minus 0 is also A. So that's a really handy way to use this as a buffered mult. If you have just a straightforward buffered mult, that will also work just the same, but I prefer SumDiff because it has additional features. Next, we have lapsus os, which is a 4-channel attenuverter. We'll only be needing 2 channels of it here. But it's got unipolar and bipolar modes. You plug a signal into it and then you get the signal out, and the slider will attenuate the signal when it's in unipolar mode, and when it's in bipolar mode, the 0 point is sort of right in the middle, and going up will be the sort of positive attenuation of that signal, and if you go below the middle point, it will increase the signal level but invert it at the same time. And so we can use that as our inverter. And finally, we've got Hive, which is just a simple audio mixer that we can use to mix the 2 outputs together. Okay, let's patch this up. So the first thing that we're going to do is we're going to take our audio output signal from A instead of B, and then we're going to patch output B directly into our mixer. So that right there takes care of the normaling from A to B. We now just have the 2 channels of amps mixed together. Next, instead of taking the 2 signals from Ona and plates and plugging them directly into the input of amps, we're going to need to multiply each one. So we're going to unplug the signal from Ona. We're going to plug it into our A input on the sum diff. And then we're going to take 1 copy of that, plug it back into A input on amps where we originally had it. And then the next one, we're going to plug into the first channel of lapsus os. And the output of lapsus os, which again, in bipolar mode with the slider all the way down, will be an exact inversion of the input signal, will get plugged into B on Intellijel Amps. And then we're going to do the same thing with the signal from plates. So we're going to unplug the original CV input from amps, plug that into the C input on sum diff, take 1 copy of it into the CV input as it was before, take the other copy, plug that into the second channel of lapsus os, again fully inverting the signal. And then we'll take the other, that inverted copy and plug that into the B side. And we just have to switch these switches back into their original position so we're not doing additional inversion on amps itself. And now when we listen to the audio, we've got that ring modulated signal once again. Of course, we are still using amps, but at this point, we're just using it as a simple VCA, and its extra features are not in play. So this could be done with any 2 channels of VCA that you might have, as long as you have these extra utilities to do the multiplication, the inversion, and the mixing for you. The last thing that's worth mentioning about ring modulation is that I've been demonstrating it here with just sine waves, which consist of a single harmonic. But the cool thing about ring modulation is that it actually applies to every harmonic of the original input signal. So if you use a more complex wave, like a saw wave or a square wave or something else, then you'll get a very rich tone that changes significantly with different frequencies from the carrier, which is the primary oscillator, and the modulating oscillator, which is the one that causes the ring modulation. So let's switch over to a couple of these other outputs on Ona and listen to the sounds. So if I go from the sine wave to a saw wave, then we got a much richer sound. How about a pulse wave? And we can modulate the pulse wave and get different sounds. And of course, we can also change the modulating wave as well. And the more complex we get with the modulator, the more wild harmonics we'll get with very different tones. I hope this video helped you to understand ring modulation better. I certainly learned a few things while making it. If you found the video useful, I hope you'll subscribe to the channel for more videos like it. I would also very much appreciate your support on Patreon. You can join for free for updates about new videos, or chip in a few dollars a month for a bunch of benefits, like high-quality audio downloads of music from the channel, patch notes for educational videos like this one, sample packs, full access to the community Discord server, and more. Thanks so much for watching. I'll see you next time.